Backyard Roller Coaster STEM class, part 2. We talked about the law of conservation of energy. Can't be destroyed, can't be created, can be converted from one type or another. There's lots of types of energy, some considered kinetic or moving energy, and some considered potential energy. There's all kinds of different energies, but basically those fits in those two categories. So potential energy, for our purposes in roller coaster design, we look at potential energy and kinetic energy. Potential energy is simply the mass times the height times the gravitational constant, which is always the same when you're on the surface of the Earth. That's 9.81 meters per second squared. You look at this equation, so what engineers and scientists, once they have an equation, once they've derived an equation, they look at it and we see, let's see, what's the relationship between the independent variables over here and the dependent variable, the potential energy. We're changing the mass and the height. If we're staying on the Earth, G is always going to be very close to the same number, 9.81 meters per second squared. But if we double the mass, then our potential energy doubles. If we take half of the mass, then we get half the potential energy. Same with height. Double the height, double the potential energy. Half the height, half the potential energy. Looking at kinetic energy, that's a different equation. It's equal to 1/2 mv squared, where m is mass and v is velocity. So the faster something's going, the more kinetic energy it has. But it's not a linear relationship. I've drawn a graph down here. This is an independent variable and a dependent variable. So this would be mass and height and velocity, and this would be the kinetic or potential energy over here. Potential energy is a linear relationship. And so if you double, like I said, if you double the mass, the kinetic energy doubles. And you plot that out, it becomes a line, and we call it a linear relationship. Kinetic energy is a nonlinear relationship because it has this squared term in it. And that means velocity is kind of more important than mass in this equation. In other words, if you double the mass here, then the kinetic energy doubles. But if you go from, say, 1 velocity to 2 velocity, you double the velocity, then in the case where the velocity was 1 and then you change it to 2, the kinetic energy actually goes 4 times its original amount, because 2 squared is 4. So engineers and scientists, we always look at these equations and say, what's important here, what's less important. So we're going to design a roller coaster, and we're going to make it simple, just 2 dimensions. Not going to have turns in it. It gets more complicated with the math and everything with turns, but certainly we can do that. But to make it simple to understand what's going on with energy, we're going to start at a high level, h3. We define 0 as whatever the lowest point is. So our height, number 3, we start at that. We go down and we pick up speed till we're going a pretty fast velocity, and we've changed a lot of potential energy into kinetic energy. And we don't have much loss. Once we get to this point, we have lost a little bit of, we've changed a little bit of energy through friction, of air friction and mechanical friction, to heat. And that's what happens. You either change it to, wind or friction. It all eventually comes down to heating up the environment that this is in. And then we go up here and we trade some of the high kinetic energy we had down here when we were going fast, and we change some of that back into potential energy. So at this point we have some potential energy, some kinetic energy. You'll notice the heat change, due to mechanical friction and aerodynamic friction, always goes up the longer you go. And ultimately, when this thing settles down and is at the bottom of this dip and not moving at all of the energy was converted to heat via mechanical or aerodynamic friction. We keep going, and then we go down to the lowest dip, and we're probably going the fastest here, so we have the most kinetic energy and the least amount of potential energy. And then we come up to some point. We're trading this kinetic and potential energy, and then we go back. We may go over this hump and go over it again, but it's just trading potential and kinetic energy all the time, seeing a little bit of a loss because of friction. And so we can actually calculate these numbers and design this before we build it and test it. We can know what's going on here, and we can see what the ride's going to be like, or predict what it's going to be like and how fast we're going to be going, and how many G's we're going to experience via the radius. We'll talk about that in a minute. But we can model mathematically our roller coaster before we ever build it. And if we don't like it in the model, we can change it. So equations are just modeling of the physical world. Newton's law of universal gravitation. Turns out it's a fact that two masses attract each other. There's an attractive force between two masses. This is universal. There isn't any mass that's not subject to this that we know of. At least in a Newtonian world. I don't know about advanced physics. Maybe they would say something different. But for what we're doing here, we have one mass, we have a second mass, and then we have a G, a gravitational constant. I'm not sure what the number of that is, but it's for the Earth and anything on the Earth. There's one number that suffices here. And then the R is the distance between the centers of the two masses. So if I'm standing, my mass is close to the Earth's mass. My mass and the mass of the Earth go into M1 and M2. The R is the distance between the center of the two masses, between the center of me and the center of the Earth. That's that distance. And that will give us a force. Okay, and that's what gravity is a force between two masses. So look at this equation. So if I double my mass, I weigh twice as much. And if we double the mass of the Earth, I would weigh twice as much. But if I get far away from the Earth, get up in space, then this number gets really big. And so because it's in the divisor, it's down here, the bigger this number is, the smaller that number is. And so if you get far away from the Earth, then this is a real small number. Okay. This changes. If you go in a mine down into the Earth, this equation changes. Because at the center of the Earth, this number would be 0, and so you wouldn't weigh anything at the center of the Earth if it was possible to go to the center of the Earth, which it's not. It's too hot. Anyway, that's Newton's law of universal gravitation. So gravity is a force vector. A vector is a quantity of force, and it's got a direction. Okay, for our purposes, it's just in a 2D plane, so we can draw it. This always points toward the center of the Earth when you're on the Earth, and it has a constant value of 9.81 meters per second squared. That's the value of the gravitational constant when you're near the center, near the surface of the Earth. So a gravitational vector always points down. In fact, I knew an engineer, and whenever someone would say, "What's up?" he'd say, "The tail end of a gravity vector," which is the definition of up. That's a joke that engineers get. So gravity is pushing us down, and that's a force. There is a force because the Earth is solid. There's a reaction force that pushes up on our feet, and that's why you don't move anywhere, is because those forces balance exactly. If we want to know what this force is, we use Newton's equation. Force equals m times a, where acceleration is g, 9.81 meters per second squared. We take our mass in kilograms, and then we know what the force is that we're pushing on the Earth and the Earth is pushing back with. and that's in the units are newtons. We call that force weight. So this is something when a roller coaster rolls on a track, a curved track, then the resultant force or the deceleration of the mass is like I'm depicting here. This is the normal force. A track can only exert a force on a wheel normal to that point in the curvature of the track. Gravity always goes down, so the resultant of that is this either acceleration or deceleration. If we're going down a hill, it's accelerating at this rate. The way you find that out is you can make a little triangle out of it and figure out the trigonometry of the angles and stuff, and you can determine how big that is. So obviously the steeper the track is, the bigger this blue force is, and the bigger the acceleration is. And if you went to the bottom here, it wouldn't be accelerating at all. It'd just be going at a constant velocity, because this blue vector would be 0 once this wheel gets down to the very bottom. And as you get into an upturn, then the opposite happens. I need to go backwards. So I think that's that. So we know the equation for centripetal acceleration. So in other words, when you're going around a curve, like we saw previously, when you're going around this curve, there's an acceleration happening there due to gravity. And this is the equation for centripetal acceleration. Look at this equation. Acceleration is toward the center of the circle that you're traveling on. So this is acceleration is in this direction, upwards toward the center of the circle, and the reaction force, which is you pushing on the roller coaster, goes in the opposite direction. Okay, and if you were swinging a bucket of water, that would be the reaction force. You'd be swinging it in a circle, and the acceleration would be towards the center of your shoulder, and the reaction force is the water pushing on the bottom of the bucket. And that's kind of how it does. Now look at this. Acceleration equals velocity squared divided by r. So the bigger the radius, the smaller the acceleration. Okay, and if you have a big radius track, then the accelerations are smaller than if you have a real tight radius track. Okay, velocity squared, again, velocity is important. If you as opposed to 1 meter per second, if you're going 2 meters per second, then the acceleration is really 4 times that. So it's another one of those things that's a nonlinear relationship. We can do this experiment, and maybe you want to try this. This is first out, we work out the math of it, and then we do the experiment. So we want to know, if I had a bucket of water, how fast would I have to spin it so the water wouldn't fall out? Okay, when it's right at the top, we don't want the water just barely to be sitting there and not falling out. So how fast do we have to spin this? Our equation is acceleration is velocity squared divided by r. We do a little bit of algebra. We divide both sides by velocity. We times both sides by radius. And then we get AR equals V squared. And we can change that. We can take the square root of both sides, do a little bit of algebra, and we get velocity equals square root of A times R. And this is where math really comes in handy, because we wanted to know what the velocity was, and we just had to manipulate that with our algebra. So the centripetal acceleration toward the center of the swing has to be greater than the gravitational constant. So when this bucket's right at the top, we want that acceleration to be equal to 9.81. Okay, and then the water will stay where it is, it won't fall out. If we're swinging slower than that, the water will fall out. If we're swinging faster than that, the water will certainly stay in the bucket. But so we need to have it, we need at least a certain rate of RPMs swinging this over our head. So I'm just going to say the radius is 0.75 meters. Roughly a meter's a little shorter than a yard, and so a meter's about probably what a lot of people's arm length is. Just to make things easy, we're going to say radius is 0.75 meters. That's pretty close. You can measure that on your own arm before you do this. That's the circumference of the circle. Okay, you're swinging this in a circle, that's the circumference. So that equals R. V equals square root of, we use our little derived equation, the velocity equals the square root of 9.81 times 0.7 times, and we get 2.71 meters per second. That's the velocity we need to be going at the top of the circle, so the we produce the right amount of centripetal acceleration to counteract gravity. Velocity is distance divided by time. We solve for t, both sides times t, divide by v, both sides. We end up with time equals distance divided by velocity, or time equals their circumference divided by radius. Circumference of the circle is a distance, 2 pi r. That's, remember, an equation, 2 times pi times r is the circumference of the circle. That, in our case, where r equals 0.75, pi is 3.14. Our circumference, I'll call it c, is 4.71 meters. The time for one trip around the circle is 4.71 divided by 2.71 equals 1.74 seconds. So we need to swing this bucket around our heads every 1.4 seconds, which is equal to 104 cycles per minute. There's a 60 in there, so we times that by 60 and we get 104 cycles per minute. So every minute we have to swing this bucket over our head 104 times. Using a metronome, you can swing at this frequency, and you'll see somewhere in there, about there, the water stays in there. And then if you want to slow down a little bit, you'll see, oh my gosh, water's falling out of it, and you get water all over you. Very fun experiment for you to do. So back to our roller coaster, in the first dip, we don't want to go too fast, or else we'll have too many G's. And so if we say the most we ever want to do at the bottom of this first dip is 4 G's. 4 G's means 4 times the gravitational constants, which means 4 times 9.81 meters per second squared. And roughly that's 39 meters per second squared, which is about as high as any roller coaster will go for a short time. You can take really high accelerations for a fifth of a second or less, but if it gets to be a couple of seconds, then it starts to make the blood rush out of your brain, and they will go some number of seconds at 4 G's, and that'll make you start to feel lightheaded, and that's what you feel on a roller coaster when the blood is kind of rushing out of your head because it's being pushed down by the gravity and the centripetal forces. So we work backwards on that equation, find the speed needed for a reasonable track dip radius, which equates to a downward acceleration of 3 G. So we subtract 1 G for gravity. We always have 1 G on us, and so the track is going to make a centripetal acceleration of 3 G's. So total is 4 G's. That's how they talk about, when you talk about G forces, it's always with the 1 G added. So 1 G times 9.81, 3 G's is 29.43 meters per second squared. Now, we have this equation, acceleration equals velocity squared divided by r. We change that. We multiply both sides by r, then we take the square root, and we get velocity equals square root of acceleration times radius. Now we pick a reasonable dip radius of 1.25 meters. Now we can change that, but I'm just saying we're picking that. 1.25 meters is for a backyard roller coaster is a reasonable number. And our velocity, we plug this in, we plug the acceleration in, we plug the radius in, and the velocity is 6 meters per second, which is pretty fast. I think that's 20 miles an hour or something like that. So the height required to give us this speed is calculated by taking, we want to know how high this, in order to get 6 meters per second in the dip, how much elevation do we have to make that kinetic energy equal to the potential energy we start with. So now we can calculate that. We say kinetic energy, this is the kinetic energy, the velocity is 6.065 at the lowest point, the dip. And we say, okay, we know how much kinetic energy that is. What if that's equal to the potential energy, and that equals mgh? So we come up with this equation. Kinetic energy equals potential energy. We do some algebra. The masses, we divide by m, mass on both sides. We get this equation. Interesting that mass drops out. That would mean in a perfect world, it wouldn't matter if a child or a great big adult, it would be the same for a small mass and a big mass. It's not quite the same. We'll talk about it later. So we solve this equation for h, which means we divide both sides of the equation by g, and we come up with this. We plug in the numbers. We come out with a height of 1.875 meters. And that's pretty reasonable. We could build that in the classroom or outside, and nobody's going to get too high to get hurt while we're building it. And we conclude that a 1.87 meter high vertical height difference between the start and dip with a 1.25 meter radius in the dip will give us 3 G's of centripetal acceleration. Add 1 G for gravity, we're at 4 G's. A 100-pound rider will feel like he or she weighs 400 pounds in that dip. That's how you calculate that. So for a short amount of time, you're going to feel like you're really being pushed into that cart. So there we are, back to our design. We know this is going to be about 1.8, almost 2 meters. So 2 meters vertical height from here to here. I think we'll stop there and pick it up with the negative G's on the airtime hill in part 3.